Welcome back to our third and last part of our webinar today. C-Protect Distance Protection Special Applications.
And there you can see a power transformer, not normally what we will be protecting with a distance protection, but I will show you here that we have got a special function, impedance protection for that purpose, and also show you the reason and the advantage of that compared to a distance protection in this environment. And for that purpose, I've used a example, and this example will follow basically, the step-by-step engineering, which is standard with C-Protect 5, and you can get, by combining different functions, a very effective and efficient solution optimized. So you don't have to really make compromises as one used to do in the past. You can really choose the best function for each purpose as you need it. An example I'm going to use to show this is what you see here, a typical medium voltage transformer. This example 20 MVA, and you'll find that typically, especially to what we see in the bottom here, the renewable generations, often these transformers are reaching their limits, and nowadays often in this environment where it used to be 20 MVAs, one goes up to 40 MVA to make allowance for not the consumption down here, but the generation in some sense, which creates new difficulties in applying protection. But let's go for it step by step and not get ahead of myself, as I sometimes do. We are applying here a relay, all right. I'm calling it a relay because it's not only a distance protection, and this relay is applied here on the LV side of the transformer. This is very commonly done in some utilities, and I'll show the advantage and the reason for this and the really strength of having this application. This relay has got two primary functions. One is to do protection in the direction towards the medium voltage system, but also to give some backup protection for this transformer for certain in-feed conditions, especially from these renewables down here. And we'll look at this here. We'll apply a zone 1 into this area and a zone 2, again 2 zones, but these 2 zones have got a different requirement as they would have had what we spoke about this morning, the zone 1-2 selectivity on a normal application. This is a different application of the distance protection. The zone 1 you see here is backing up the busbar protection, because here on the medium voltage you typically won't have a busbar protection, but you want to obviously have fault clearance of the busbar protection as fast as possible, and we'll do that with a reverse interlocking scheme down here. And the zone 2 is doing backup protection for these feeders, and that is an extremely important function, which we'll see just now again. It is not just backup, it is backup, very important. Then we have the zone 3 backup for the transformer. Maybe you have 20 MVA. Could be, sometimes people would put in a dedicated transformer differential there. Some people would not. It's on the boundary. Depending on some, it's a transformer size decision. Doesn't really matter. But anyway, you can have this protection also doing backup for the transformer. And this backup is in 2 zones, 3 and 4. One is an underreaching into the transformer, and the zone 4 even reaches up here for certain conditions through the transformer. And we'll see there is special requirements here. Normal distance protection might not be ideal for that transformer backup. But before we get there, let's go step by step. The zone 1, a busbar protection as such, done with reverse interlocking, that you can coordinate with the feeders. So the reverse interlocking principle will get pickup signals from all the feeders here, which would block here, and this zone 1 must be coordinated with these down here, that it does not reach into an area where it will not get blocked, then it would be not selective. So the purpose would be that it would see the busbar fault surely. It will also see some other faults in the feeders, but if it sees a feeder fault, it will get a blocking signal from the feeder protection. So the feeder protection must be more sensitive than the zone 1 over here. That is the requirement for the reverse interlocking. The zone 2 over here is doing a backup protection for these feeders. And as I said, this is a very important, maybe the most important functionality of this protection here, is because these MV bays will have a single trip coil, a single protection, and basically no backup. There's not a main 2 on a medium voltage feeder. It's only a main 1. So if there's a failure of this protection, or if there's a failure of the breaker, the trip coil or something on the feeder over here, there must be a backup. Somebody must do that. And this is the task of this transformer in feed. This transformer in feed is one would call that a remote backup for this feeder, but it's not the same relay. It is kind of a little bit remote from where that feeder is. Backup functionality. And that is a difficult task, as we'll see later on over here, because it needs to get a very sensitive setting in the distance protection. Then we're going to have here this transformer protection, as I said, an underreaching zone 3 into the transformer as a backup transformer protection, and a zone 4. The difficulty here is, especially if you look at the zone 4 protection, the fault on the other winding here will be decoupled. The transformer will remove, for example, the zero sequence, and you would not get any zero sequence from the top system coupled into the bottom. So if there's a ground fault here, there will be no zero sequence voltage or current on the LV side, which can be difficult. Remember, we're expecting sequence components in a normal protection as such. The zone coordination is then the next step we will look at. Okay, so we've clearly identified what we are doing here. This relay is applied here on the LV side of the breaker, and it's really got a multiple tasks to do. And how are we going to implement all those tasks here and get the job done? Starting off with the zone 1. The zone 1, as we said, must be sensitive, but it may not overreach what the feeder protections are seeing. So we must check the feeder protection, and here you would have an overcurrent setting. And we remember this morning we had the circle characteristic. And the circle characteristic was defined by a voltage and a current. And effectively, we can draw this overcurrent protection here as a circle characteristic, where the radius of the circle is defined by the overcurrent setting of this relay. And we can coordinate our zone 1, that the zone 1 does not overreach that. And that way, we are sure that the zone 1 will not pick up for a fault that the feeder protection cannot see. It's a very, very high security in this for our bus bar protection, what we want, but we don't want accidental bus clearance for a feeder fault, and that we get done in this job. So it is really fairly, and we don't need a really big zone 1 setting, but the zone 1 setting must only cover the bus bar fault. The biggest difficulty for the zone 1 is to get sufficient resistive reach for a resistance fault on the bus bar. All right, the difficult one is the zone 2. The zone 2 must see a remote fault on the feeder. If this feeder protection fails, maybe there's a breaker failure, maybe the relay has failed, there's power supply failure in the feeder relay, then we need to have a trip by the backup, which is the transformer in feed. Otherwise, nobody feels responsible for it. Who's going to clear this fault if the feeder protection has failed? We have to rely on the backup protection. All right, and that is difficult because we have a coordination of load and fault in feed. You can see here at the bottom, the feeder might have a 300 amp load current, and the according setting may be set to 400 amps to coordinate with the load, tripping at 400 amps down there, and the fault, the load current on the transformer, all the feeders in parallel. If you have a 40 MVA, I can now see I've gone up to 40 MVA with the transformer, but that's typically what's happening. You get 1000 amps full load current, all the feeders in parallel, but each individual feeder only 300 amps. And you have to get a pickup. And this, you can see if using the RMD technique, as I mentioned earlier on, the load cutout, you can set the load cutout, but this load cutout will only cut out 3-phase faults, for example. And that's the advantage of using the RMD technique, even in an application like this, compared to a classic distance protection. All right, this is what you can see here. For example, a face-to-face fault. We would see a face-to-face fault in here. The RMD can pick up, even though it is inside the load area of the impedance, the RMD technique will trip for that fault condition. And we want to go through all the calculations here, but it's just the principle to show you that you can get a good sensitivity and you can get tripping inside. You can set the load cutout that would apply to 3-phase conditions. It's a small limitation, but we don't typically would get 3-phase faults over here. 3-phase faults are normally if you're switching onto grounds and so on, but over here remote faults with backup requirement is typically asymmetrical faults. The 3-phase fault, in the 3-phase fault we would normally have a larger current and we would not be in that area. The 3-phase fault would be a bolted short circuit with a small resistance which we would then cover inside the reach. Effectively this single phase to ground faults and so with the fault resistance you see the problem, but that goes in this area, but those we can detect even if they are inside the load, because the load cutout only applies to 3-phase faults if you apply RMD. Okay, now we come to the more difficult situations here, sorry, we're still with the face-to-face fault down here to showing you that the load cutout here will not be affected by that. Design 2 can detect that fault inside the characteristic, because remember the RMD technique is detecting this would not pick up on a load here, but can detect on a fault because the substitute current is based on negative sequence, and during load we don't have negative sequence, so it will not pick up on the load condition, but the fault condition it will pick up inside the characteristic. That's why the RMD can trip for faults inside a load cutout if it's an asymmetrical fault. Sorry. One slide ahead now. Now I'm at the slide I thought I was at. Now we're at the transformer backup. This creates new difficulties for us, okay? Because we are now looking into a transformer, and this transformer, here we have a star delta transformer. It would also apply to a delta star transformer. Also star-star transformers if they are not both grounded, but those are unusual. Y transformer with 2 grounds is unusual. If there's a delta in that, like you would have an auto transformer, the delta would also shunt the zero sequence to a large degree. The zero sequence would not come through that transformer at all. So we typically will see on power transformers that if you have a ground fault on the one side, the zero sequence will not be coupled through to the other side. And remember in our loop selection, that was an important requirement for loop selection, that we get a single phase loop can pick up only if we have a ground fault detection, for example. So normal distance protection is not always going to be ideal over here. In this diagram, we see just a little example here, and you can see at the bottom, the top is a circuit diagram. If you don't want to look at it in detail, you can see the L1 voltage at the top is over here. It's pointing down here. Look at the red arrow down to the fourth quadrant, or basically look at the angle. It's at, if you think of a watch, that's the center of your clock, then it's pointing to about 5 o'clock, right? And if you look at on the left-hand side, the star side, the HV side, the L1 voltage is at 12 o'clock or 0. This would be a YD5, okay? Because the Y is at 0. And on the delta side, the LV side, you can see the L1 voltage is at 5 o'clock, just for an example. But that's not important for us now. What's important is the bottom diagram. So the bottom diagram, you can see our relay located on the LV side, the delta side down here, is measuring this, and we have now applied a fault on the HV side, and we've applied a L1 to ground fault. And you can see the red phases show you the loop current flowing through that L1 to fault. There's current flowing out on the L1 through the fault and back in via ground. That is the loop on the HV side over there. And then due to the transformer coupling, that couples onto the delta side, and you can see there's current in this limb, so we will have current flowing out here on that phase, L1, and the current is flowing in here on L2, but it's not flowing, cannot flow through that limb because there's no current on the other side. Transformers must be balanced in ampere turns. The current is flowing on that bottom path up there similarly. So we get a phase-to-phase current here. It's clear we cannot get a single phase current on the delta side. It cannot just flow in. There's no star point return. So we see here we have a phase-to-phase current, L31, during an L1 to ground fault on this transformer. So the loop that we need to measure with, the loop that we need to measure here is the L31 for L1 to ground fault on that side. And this would work in a classic distance protection, would be able to do this. So one, say some cases, the classic relay would see the voltage drop here in the loop L31, and it'll see the current in L1 and L3. So a normal distance protection could deal with this fault. It would work okay. Pick up there. Here you can see just the example, all the phases shown, the top, basically the UL1, and basically the voltage that side, the current this side. You can see pre-fault no load current, okay, pre-fault voltage, and then the faulted voltage here, and then the fault current, and then at the bottom you can see at the bottom the phase-to-phase current, L31, and on the HV side the single phase current. But this is, as we saw in the previous diagram, as expected, and you can see the voltage here, the phase-to-phase voltage, sorry, the phase-to-phase voltage, I should have probably drawn that, the L31 phase-to-phase voltage is the smallest one together with this loop current here, would be okay for a classic distance protection. So you think, all right, that's very good and well, and that is going to work, and we would measure an impedance. I measured impedance I showed now in the bottom here, as one would expect a reverse fault. But remember, in our relay settings, we defined the forward was into the 22 kV network, and reverse was into the transformer. So the reverse zones into the transformer would pick up on this. So we can pick that up, and it would measure 1.5 times the transformer reactance. That's something one must be careful of. The single phase fault on the star side is measured at 1.5 times the transformer reactance on the LV side. This is what you know, because there's some current disappearing into the zero sequence circulation here. That's the typical condition you will have. Nothing special there, but now we go on to the problem condition. What if the fault on the HV side is not a single phase ground fault, but a two-phase fault? Here in this example, L23 fault. Now in this L23 fault, you can see again the loop current flowing out here on L2 and in on L3, the two arrows on the HV side, and they couple then through the transformer to be a current here. And now we get a strange scenario. The current is flowing out here on the center limb. Okay, it's coming in from the top, but it doesn't flow through that winding. Obviously, there's nothing on that winding there, so the current flows here to the star and out, the one arrow. And the other one comes here, must match the current that we have on the other side here, flow in on this side to match that current through here. And so we've got two currents coming out here, one in, one in. No zero sequence. It's important. Even on the previous diagram, remember we had a phase-to-phase current on this on the LV side. Here we've got two in, one out, or two out, one in and out here. So it's four, one going in, and two coming out. If you summate them, there's no zero sequence. No zero sequence current, no zero sequence voltage. And yet, we want to measure with a single phase loop. We want to measure with L2 ground. The correct loop to measure an impedance here is L2 to ground loop. A classic distance protection will not be able to do this, because a classic distance protection, to select a single phase loop, the L2 ground loop, it must have zero sequence. It must have ground current. So for this, that's why I said on the transformer, we should use the dedicated impedance protection. Because impedance protection will be able to look into the transformer with the zone 3 and 4 and be able to choose the correct loop without having to see zero sequence current or voltage. Because the zero sequence current voltage is decoupled, removed by the power transformer. It is not coupled through. In the project tree, if you look in the project tree, you can see the distance protection. You can use distance protection classic or RMD I would use, recommended here, the RMD technique. And you set that for your zone 1, zone 2, which are looking into the medium voltage system. And for your zone 3 and 4, looking into a transformer, you can see down here there's an impedance protection for transformers, which you can apply in parallel. And you can apply both in the same function group, the same line function group we applied there. And they would use obviously the same current and voltage, but there's two functions doing two different jobs.